So in the last class, we were talking about implementing our own string type. So we got a string type called QString. In the last lecture, we looked at a bunch of functions that initialize a QString object. And we have some functions that access information in the QString object, but they don't change they don't change the size of the underlying array. And so if you're implementing a string type, you're probably going to want functions that do change the size of the underlying array. So for example, the function assign assigns the string pointed at by the right-hand side to the string pointed at by the left-hand side. Now, if the length of the string in right-hand side is greater than the capacity of the string on the left-hand side, you have to resize the array belonging to the left-hand side so that you can store the string in that array. Similarly, concatenates the string LHS and RHS, so left-hand side and right-hand side. And I think it concatenates the right-hand side onto the end of left-hand side. So it's similar to the C string concat function, except our concat function will automatically resize the array on the left-hand side if required, right? And so in other words, if the length of LHS plus the length of RHS is greater than the capacity of LHS, we're going to increase the size of the array belonging to LHS, right? And so it looks like there's going to have to be some memory allocation going on. Every time you do memory allocation, you have to check if the allocation succeeds, yada, 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 yada. So instead of writing and repeating all of that code, it's useful to insert a function that actually guarantees a QString object has sufficient capacity. So our function ensure capacity makes sure that the string pointed at by S has at least capacity given by the argument capacity. If it doesn't, it expands the size of the array so that it's belonging to S so that it has the required capacity. It's not hard to implement in qstring.c, so it's all the way back at the top. So here's ensure capacity. Right, so we want to make sure that the string pointed at by S has at least that much capacity. So we check, right? Is the capacity of S, is it greater than or equal to the specified capacity? If so, we don't have to do anything, right? So we just return S. Right. Now, what happens if there is not sufficient capacity? Well, we have to reallocate the array belonging to S. Right. So remember that array is called data. So we use realloc to reallocate that array so that it has at least that much capacity. Right. We're calling realloc. So if you're being paranoid, you're going to check, is the pointer returned by realloc null? If it is, there's an error. We're going to return null. Right? If there isn't, right? If there is no error, we have a new array which we can assign to S. Right? So S's data array is now equal to the newly allocated array. Right? S now has increased capacity, and now we can return S back to the caller so that they can use it, perhaps passing it to another function. So there's ensure capacity. With ensure capacity in hand, implementing assign and concat are relatively easy. So looking at assign, we're going to do some error checking first, right? So if the left-hand side is null, then we're not going to try to concatenate to that string. That's going to cause a problem, right? If the right-hand side is null, or if the left-hand side and the right-hand side are the same thing, we're not going to do anything either. Okay, so otherwise, we're going to try to concatenate whatever's sitting in the right-hand side string onto the end of the left-hand side string. Right. So how much capacity do I need? Right. Oh, sorry, this is assign, not concat. Right. So we're going to assign stringing the contents of RHS into the array belonging to LHS. Right. So we have to make sure that LHS has sufficient capacity in its array. So we call ensure capacity to make sure we have sufficient capacity, right? How much capacity do we need at a minimum, right? So at a minimum, we need the length of the right-hand string, right? +1 for the null terminator, because we're always null terminating our strings, right? You could also write RHS capacity instead here, right? Because we know that the right-hand side has sufficient capacity to hold its string. So either one would work. I'm using the minimum amount. It doesn't matter which one you do, I don't think. Right. So we ensure that we have sufficient capacity. If we get back null from ensure capacity, we know that allocation failed. So we're going to abort and just return null, indicating that we can't actually complete this operation. Right. Okay. So you might try to do the following. Right. So you might say, hey, look, our string is just a C-style string, so it's null terminated, right? And so to copy the contents of right-hand side into left-hand side, we can just use string copy, right? However, our string type doesn't actually have the constraint in it that it's terminated with that the null terminator indicates the end of the string, right? Our strings are null terminated, so that means after the last character in the string, there is a null terminator. But some of the intermediate characters are allowed to be the null terminator. If you use string copy, you only get up to the first null terminator copied into the left-hand side. So instead, what are we going to do? Well, we're going to copy it ourselves. How are we going to copy it? We're going to use memcopy. Right. So I'm going to copy the data belonging to the right-hand side into the array belonging to the left-hand side. How much am I going to copy? I'm going to copy the length of the right-hand side string +1, right? The +1 gives me the null terminator belonging to the right-hand side. And so that null terminates the left-hand side as well, right? Once you've done that, go ahead and set the length, right? We don't have to set the capacity, right? The capacity was set back up here if I ensure capacity, right? And then finally return the left-hand side. And so there's assignment, right? The reason you need this function is because if you have two strings, so remember our two strings, we're always using pointers to structures. So if you just write S1 equals S2, all you're really doing is assigning one pointer to another. You're not actually assigning a string to another string, right? You're actually changing your pointer, which is not what you want to do. So if you want assignment, proper string assignment, you go through the function QStringAssign. Okay, so what about concat? So concat takes whatever's on the right-hand side, sticks it on the end of the left-hand side, and then makes sure that the left-hand side is null terminated. Almost exactly the same as before, right? So do some error checking first, right? Compute the required capacity. So how much capacity do I need for the concatenated string? It's the length of the left-hand side plus the length of the right-hand side +1, right? +1 for the null terminator again. So that's how much capacity I need in the left-hand side. How do I ensure we have enough? Well, call ensure capacity, right? So make sure we have that much space in the array belonging to the left-hand side, right? If we don't, ensure capacity will add the extra capacity for us. Right now, we need to copy or concatenate whatever is belonging to the string on the right-hand side onto the string onto the end of the string belonging to the left-hand side, right? So starting at the front or at the beginning of the array belonging to the right-hand side, I would like to take that data and stick it on the end of the string on the left-hand side, right? And so the end of the string belonging to the left-hand side, right, is the start of the array. So that's left-hand side data plus the length of the string. So that's left-hand side length. Right, and so that is the pointer to the character at the end, one past the end of the left-hand side string. Right. How much data am I going to copy? I want to copy all of the right-hand side +1, so I get the null terminator. Okay. Mem_move. Why are we using mem_move? So you could, I guess your first inclination might be to use memcopy, right? The correct thing to do here, though, is to actually use mem_move. Right, and so why should you use mem_move? Right, it's because our version of concat, right, does not have the restriction that the left-hand side and the right-hand side be different strings, right? So in other words, our function lets you concat a string to itself, right? So you can write q string concat s comma s, right? And that basically duplicates s onto itself, right? So if you had the string hello, it'd be the string hello, hello, right? The standard library implementation doesn't let you do that, right? So strcat, sorry. You can't concat a string onto itself. Our string you can. The reason you can is because we use memmove, right? Memmove lets the memory being copied overlap into, lets the memory that's being copied overlap with the memory being copied into, right? Which is what we need if we want to concat a string onto itself. Right. Last step. Don't forget, you just added stuff to the end of the left-hand side, so you have to change the length of the left-hand side, right? So it's now equal to the sum of the two string lengths, and you're done. You don't have to change the capacity again, right? Capacity is set by ensure capacity. And so those are the two functions that modify a string, right? If you wanted to, you could add a whole bunch of other functions here, right? So for example, you could remove a character from a string. So to remove a character from a string, you don't have to worry about the capacity of the string. You're going to remove stuff, so you don't have to increase the capacity, right? But now you have to figure out, how do I shift the characters in the string over one position so that I can remove a character, right? The answer is use memmove, right? You want to move the end of the string over one position so that you cover up the character that you just eliminated, right? And so that's pretty easy to implement if you're comfortable using memmove. And there's our, oh wait, there's one more function to talk about. And so we've got functions that create new strings for us, right? So that's the functions that we looked at in the last class. So make a new string, right? Make a string from a C string, make a string from another string, right? These all end up calling QStringAlloc, right? And remember, QStringAlloc, what does it do? It allocates memory for the structure itself, right? And then it allocates memory for the buffer, right, for the data array. And so if we want to clean up after one of our QStrings, so when we're done with our QString object, we have to get rid of the memory that's associated with the QString object, right? So you have to free its array, and you have to free the memory that was associated with the structure itself, right? You could make the user of the class of the structure do this, but it's nicer if you provide a function that does this for them, right? And so the function destroy cleans up all the memory associated with the QString object, right? Now, when you destroy the object, you destroy it from the inside out, right? So you first release the memory that's used for the object's array, then you release the memory that's used for the object itself. So we free the memory belonging to the S's array, right? We then free S itself, right? And that releases all of the memory associated with the structure back to the operating system, right? Notice that we also do some other stuff here, which is optional, but it's nice if you do it, right? So we also set the length of the string to 0, you set the capacity to 0, right? And you set the pointer to the data to null, right? And so that's, even though we free S later on, right? So by freeing S, technically the length, capacity, and data no longer exist. But if somehow the caller has a pointer or is trying to use S again, whatever they try to use it for, they're going to end up with a string whose length and capacity is already 0 and has no data buffer. Right. And that's the implementation of the string type. If you think about it for a little while, a mutable string is basically like a list, right? It's essentially a list of characters. So if you wanted to implement an array-based list in C, it's almost the exact same code, right? Instead of having a, right? So instead of having an array of car, which we have for a string, right? You just change the type to the array for your list type. So if you wanted a list of integers, right, that would become a pointer to int. If you wanted a list of double, that would become a pointer to double, right? The rest of the code is almost identical. Um, so all the operations are basically the same, right? A string is more, or a mutable string is more or less an array-based list. So that's what we're doing. If you want to try out the string, our string type, there's a little program called QStringDemo. That's part of the notes, right? And so it just uses each one of the functions that we've created, right? So new makes a new string, right? Returns a pointer to a structure representing a string, right? Destroy frees up the memory that's associated with the string. Right? From C string makes a string given a C style string. Copy makes a new string given an existing Q string. Right? Clears the contents of a string, and so on and so on and so forth. Right? So if you want to run the program, you've got to compile it first. And I think this is the first time where we're compiling a program where the program is made up of multiple files. Okay, so our program consists of qstring.c, so that's our string implementation, right? And it also consists of the test program qstringdemo.c, right? So the demo program is the one that has the main function, right? qstring.c does not have a main function, so I can put these two things together and turn it into a runnable program, right? The easiest way to do this is to just compile both of the files at the same time. And that will spit out a.out, which you can then run like that, and it spits out a bunch of information, right? The output is, you have to look back to the demo program to make sense of what the output is trying to tell you, right? But you can take my word for it, the output is in fact correct, right? And the string that we implemented does in fact seem to work the way it should. So I guess we should look at the demo program very quickly for a few things. Okay, so when you go to use the QString type in one of your other programs, the first thing you're going to do is you're going to include its header file, right? So you include the header file qstring.h. That makes all of the functions that we just implemented usable or compilable in your program, right? So as soon as you include the header file, you now have access to all of the QString functions, right? Like QString new. Is there anything else I wanted to say about this program? I guess not. I guess this is worth pointing out. So whenever you are creating objects dynamically, like we are here, so remember every QString object is made dynamically, right? You should always remember to free the memory that's associated, or the resources that are associated with the dynamically created objects, right? So if you're going to make a string, you should probably destroy the string. So if you check through the source code here, you can verify that every time a string is made, it's also destroyed, right? And that's just good programming practice. If you forget to destroy a string, that memory that was used by the string isn't released from your program back to the operating system until your program finishes. Right? And so that's worth pointing out. Even though this function or this program is made up of just a single main function, it's still good practice to free your objects when you're done with them, right? If you don't free them, then the main function just ends, your program ends, and all the memory gets released anyway, right? What else is there? Oh, there's something else that's funny about our type. So if someone, if you can include a header file, that means whoever's using this program has access to the source code for the header file, right? What that means is that they can see all of this stuff here, right? So notice what our header file currently consists of, right? The definition of the structure is right here, right? And so that means anybody who opens up this header file can look at it and say, oh, every QString has a length, every QString has a capacity, every QString has this array called data. What does that mean, right? That means in their demo, in your program, right, you can actually go into the QString and start to fiddle with the members of the structure, right? So here, when I'm fiddling around with Q3, what am I doing here? I guess we should play around with Q2 because I think I'm removing stuff from Q3. So you can go into one of your strings, right? And you can do something like q2 length equals 0, right? So you can, so the user of the type can actually go in, fiddle with the members of the type, and now perhaps put the string into an inconsistent state, right? Setting the length to 0 is not so bad. It's not the end of the world, but it doesn't make sense anymore, right? If someone prints out the Q string, it will actually print something out, right? Sure, the length is 0, right? But the data buffer that holds the string does not have a null terminator sitting at index 0, right? So in other words, the actual contents of the string haven't been set to a proper 0 length string, right? So the fact that an ordinary user can go in and fiddle with the data belonging to the type might be undesirable, right? Stuff like this would be worse, right? So Q2 capacity equals 0, or yeah, 0, right? And now your Q string apparently has no capacity, even though it has an array whose length is not 0. Right? So if someone has access to the definition of the structure, they basically have access to all of the information in the structure. That may not be a desirable thing, right? So notice how that's very different from Java, right? So in Java, Java has access modifiers on the fields and the method, sorry, of a class, and so you can prevent somebody from going into a Java object and fiddling with the fields directly. Right. Now, if you want to do, if you also want to, if you want to make sure that someone can't go into your Q string and fiddle with its members directly, there's a way to do that. Right. And so hopefully I have it at the end of this notebook. Here it is. Right. So in languages like Java, one of the important design considerations of the language was that it should be possible to hide the implementation details of a type. So a Java class can hide what fields it's using to store its information. Right. In C, if someone has access to your structure, they have access to your members as well. Right. So C has no notion of an access modifier. Right. So here's an example. Here's exactly an example of how someone can go into a QString object and fiddle with its contents. Right. Now, because C has no ability to restrict the visibility of stuff in a structure, right? There's no way that I can just mark stuff as being private or something like that. So what you have to do instead, right, is you create what's called an opaque structure or an opaque type. Right. So the way this works is the following. Right. In your header file, you simply declare that the structure exists. Right. So struct QString, semicolon says, there's a structure called QString. And that's all that it says. Right. If the user of your type only has access to the header file, they no longer know what's inside of the QString object. Right. Somewhere you have to say what is inside the QString object, right? So you have to define what the structure is. So instead, you define the structure inside QString.c. Right. So inside QString.c, you include the header file, and now you define the structure. Right. So typically if you are using someone else's C library, you typically don't have access to their source code. What you have access to is their header files. The actual compiled source code files are then given to you in some format, which you can link to your program. Right, but they can't normally see, or they can't easily see the source code for your types. Right, and so by moving the definition into the source code file, you've effectively hidden the implementation of the type from most users. Right. So by providing this, the reason it's called opaque is because people can't see into your type. Right, and so by using opaque types, whoever's creating the library gives you an interface to use the type. Right, they give you the header file, but they've hidden how everything works from you inside of precompiled source code files. Yes. So there's if you're going to turn our string type into a opaque type, then there's a few other things that you have to do, right? So number one, there's something that's missing from our type, right? There's no way for us to tell, there's no function that tells the caller how long is the string, right? To get the length of the string, we're simply relying on being able to access the member called length, right? Now you have to provide a function called length, right? But that's easy, right? There's no problem implementing that function. And similarly, if one of the design decisions of our type was that our string should be compatible with C-style strings. So you now also have to give the user access to your array of information. Right? Okay, so I guess we'll leave it at that. There's a little bit more in the notebook that you can read. There's a few extra details about opaque types that are, I guess, interesting from a security point of view. For our purposes, they're not super necessary for this course. Right? But there's an example. That's how you would convert our string type into an opaque type. All right, so we're done with that. We're done with that notebook right there. Any questions on the string type that we've implemented or any of the memory functions that we've been using? All right. I guess we should do, today is, let's quickly look at our implementing a stack now. Am I doing, I just want to, okay, so we're going to do it this way. All right. Everybody remembers what a stack is, right? Yes, yes, yes. Okay. So I'm going to assume you know what a stack is. I'm just going to jump ahead to the middle of the notebook. So you could implement a stack using an array, right? It's going to look a lot like, well, it's going to have a strong resemblance to the string type that we just implemented. Instead of using an array, I want to use a linked sequence of nodes, right? So just like in Java, you can create a type, a linear sequence, where instead of using an array, you can store the elements in a linked sequence of nodes, right? So there's a picture of a node, right? Conceptually, a node holds some information, right? So that's going to be the element of our stack, right? And then it holds a link to the next node in the sequence, right? So in C, that link is just a pointer, right? So every node has a pointer to the next node. Right? The element, for now, we're going to store it as just a primitive type, right? So if we make a stack of int, that'll just be an int. Right? So we'll start, so in Java, if you're making this node class, right, you would have one int field for the element, right? You would have a field of type node that is a reference to the next node in the sequence, right? If you wanted to make a sequence of nodes, right, you can make 3 nodes, and then you can join them all up to one another, right? So I can set the element in N1 to 1, and then I can say that the next node after N1 is N2, right? Then I can say N2 holds the value 2, right? And then the node after N2 is N3, right? And so on and so on and so forth. Eventually, your last node in the sequence has to set next to null, right? In C, it's almost the exact same code, right? Instead of a class, you use a structure, right? So instead of class node, I've got struct node. If I have an integer element, it's just int lem, exact same as in Java, right? Only difference now, right? My next member is a pointer to another node, right? So next is a pointer to a struct node type. How do you hook up the nodes given a bunch of nodes? Well, it's almost the exact same as in Java, right? So setting the elements, exactly the same, right? Setting the next link, well, it's almost exactly the same. Now we've got pointers, right? So if my nodes are actual nodes and not pointer to nodes, right? Then N1 next is just the address of N2, right? N2 next is just the average address of N3, right? And N3 next is null, so just like in Java. And so that works just fine, right? If you make a linked sequence and that sequence only needs to live for one function, you could write code just like that, right? That would work fine. Now the problem is, if you need this sequence to live for more than one function, you've got a problem, right? These all have automatic storage, right? So N1, N2, and N3, they live for as long as the block that they are defined in lasts for, right? So at the end of the block that they're in, they disappear, right? And so that means this won't work if you need to pass one of these nodes to another function, right? So what do? Well, guess what? You have to dynamically allocate the nodes, right? Once you dynamically allocate the nodes, you're working with pointers to nodes now, right? So instead of struct node N1, we've now got a pointer N1, right? So N1 is a pointer to a dynamically allocated node, right? N2, pointer to a dynamically allocated node, so on and so on and so forth, right? Now, the only thing that changes here is that, remember, next is a pointer to a node. N2 is already a pointer, so I can write N1 next equals N2, right? N2 next equals N3. Why does that work? Well, N3 is already a pointer to a node, right? And next is also a pointer to a node. So that works just fine. Right? And so if you look at this and the Java code back here, right? They're almost exactly the same. The only thing that changes is the dot and the arrow, right? Everything else is exactly the same. Okay, so how do you implement a stack if you're going to use a linked sequence of nodes? Well, it turns out it's not terribly hard, right? And if you've taken 124, you more or less know how to do this already because we've done it. You should have done it in 124, unless you took it in the summer, in which case you probably didn't. So to implement a stack using nodes, all that you're going to do is you're going to keep a pointer to the top node. You might also want to keep the number of nodes in the sequence, right? So you might want to know how many elements are in the stack. So in an empty stack, we're going to have a pointer to the top node, right? In an empty stack, there's no top node, so our pointer is just null, right? If we have one element in the stack, our pointer top is going to point to one node, the top node, right? That top node, its next link is null because there's no more elements in the sequence. Right? Push an element onto the stack, you've now got two nodes, right? So our top pointer now points at the second node, right? The second node has a link or a pointer to the original old top node, right? And its next link is null because there's no more elements in the sequence. Right, one more time, right? You push a 3 onto the stack, right? Top now points at the new node that has a 3 in it, right? That node has a link that points at the old top node, and that node has a link that points at the old top node, right? And again, the one has a next link that is null. So how do you implement this thing? We're going to do this. We're going to implement this immediately using an opaque type, right? So we're going to do this in exactly the same way that we implemented the string class, except we're going to start with an opaque type right away. And I'm also going to tell you about this thing called typedef. Okay. So an opaque type, in an opaque type, you basically have a declaration of a structure. The user doesn't know what's in the structure, right? So in this case, they're going to have a header file, I guess stack.h. Inside the header file, there'll be a structure that declares the stack, but they can't see inside the stack itself, right? Now, the fact that the type that we're using is a structure and not something else, there isn't a whole lot else in C, right? But I guess it could be something else. You might want to let the user use your type without having to type struct everywhere. Right? Whether you should do this or not is a question of style. If you want to just have a type called stack instead of struct stack everywhere, you can use typedef to provide a new name for an existing type. Right? So that's what typedef does. Typedef lets you create an alias for an existing type. Right? Alias is just another name. Right? So the way you use typedef is it's the keyword typedef. Right? you pick your name that you want to give your type. So that's your alias, right? And then the existing type goes here. Okay. So for example, if I wanted to, instead of writing struct QString everywhere, if I just wanted to write QString instead, you can make a type def, right? So type def struct QSTR, QString. All that says is that QString is just another name for that, right? Everywhere where you would write struct QString, you can now just write QString, right? So for example, instead of writing struct QString pointer course equals blah, 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 you can just write struct QString star course, right? Which is arguably easier to read than that, right? Arguably, yes.
Can you type def like the same name twice? For example, type def struct stack.
Yes,
For the type.
that is legal. Yes. So there's there's something confusing about the way type defs work. Right here, for example, there it is, right there. Right. So somewhat confusingly, right? The alias, so that name there, right, is allowed to be the same name as the tag for an existing structure, right? So struct QString, right? Remember when you declare a structure, the name of the structure here is called a tag, right? So it turns out the way that C works is that where C keeps the set of tags is different than where it keeps the set of all other names, right? So all other names include variables, functions, type defs, right? So those are considered to live in what are called two different namespaces. So the type def QString is in fact distinct from the tag name QString. So you are allowed to write stuff like that, right? And so for example, our linked stack is going to be a structure called QLStack underscore tag, right? And I'm going to type that to QLStack so that people don't have to write struct QLStack underscore tag everywhere. Yes.
So it's just the structure down to become
Yep. So QLStack is just another name. For QLStack is just another name for struct QLStack tag. That's all it means. Yep. All right. So for our linked stack, we're going to call it that. That's going to be our header file, right? So inside of our header file, I've got my type def, right? So this does two things, right? So this type def says there is a structure called QLStack underscore tag. That's the first thing it says. The second thing it says is that everywhere I'm going to write struct QLStack underscore tag, I can just write QLStack. So this thing actually does, the type def actually does two things. It declares the structure, and it also defines the name QLStack as just being the substitute for struct QLStack underscore tag, right? So that means as soon as someone imports the header file, right, the user can now write struct QLStack underscore tag if they want, right? Or they can just write QLStack. They're almost certainly going to just write QLStack. Right? Everywhere in my header file, I can now just write QLStack instead of having to write out this structure everywhere. Okay, so what's in our stack type? Well, I'd like to make, remember this is C. So if I'm going to make a stack, I have to initialize memory for the stack. I might have to initialize memory for the nodes, blah, 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 right? Instead of making the user do that by themselves over and over and over again, let's make a function that makes a new empty stack so that the caller doesn't have to worry about allocating memory by themselves. Right, so there's our initialization function. If you want to think of this in Java terms, it's just a no argument constructor. Right. Again, notice the goofy naming convention, right? It's not called init, it's called QLStack underscore init, right? Why? Because the names of all your functions in a C program have to be unique. If I just called it init, there's a pretty good chance that in a large program, that's going to collide with another function called init. Right. So all of our functions are going to be prepended with QLStack underscore. Right. Is empty returns true if the stack pointed at by S is empty. Right. Size returns the size of the stack pointed at by S. Push pushes an integer element onto the stack pointed at by S. Pop pops the element off the stack, and it also stores, and this particular function requires the user to provide a pointer to an int so that pop can write the value of the int into the object being pointed at. Right, now you might wonder why we're doing it this way. Right, and so the reason we're doing it this way is because all of our functions are returning a pointer to a QL stack. Right, we're returning a pointer because we want to return null to indicate that an error has occurred. Right, remember again in C, there's no real standard way of indicating that an error has occurred. So like there's no exception handling mechanism like there is in Java and Python. Right, so to indicate that an error has occurred, one of the ways to do this is to return something from the function. In this particular implementation, I'm choosing to return null to indicate that an error has occurred. If I'm returning a pointer to a stack, I can't return the popped element as well. So in order to give the user the access to the popped element, right, we're going to ask the user, tell us where there is an int variable around where I can write the function into. Where I can write the value of the popped element into. Right, so the popped element gets written by the function into the object pointed at by popped. Print is going to print a stack, which is going to be useful for us. And again, right, this is C, so we have to clean up after ourselves. Free is going to free all the memory that's used by the stack. Right, now to free the memory that's used by the stack, you have to free all of the nodes belonging to the stack, and you have to free the structure consisting of the stack itself. Okay, what does the source code look like? So in Java, if you were to implement this thing, it would look something like this. Right, you'd make a class called link stack. You would stick your node class inside of the class. You would keep track of the top node. Right, now remember, everything in Java, all reference types in Java, like node, are references. Right, so in C, they're just going to be pointers. Right, and it's probably convenient to keep track of the size of the stack as well. Strictly not necessary. You can just follow the sequence of nodes, count the number of nodes to get the size. Right, but it's nice to not have to do that. So if you look at that, and now if you look at our C implementation, it's more or less going to look exactly the same. You just translate everything into C. Right, so there's our node structure. Right, inside every node there's an element, and there's a pointer to the next node. Right, what does our actual stack look like? Well, it's got a pointer to the top node, right, and it's got the size of the stack. Right? So again, almost exactly the same as, it's not quite the same as Java, right? But you just have to translate the Java class into C structures, and away you go. So what does new look like? Okay, so new, well, what does new have to do? Well, new has to make a new stack, right? So use malloc, allocate memory for our structure, right? Check the return type, make sure it's not null. If it's null, return null, right? To indicate that we weren't able to allocate a new stack. Right? What does an empty stack consist of? Well, there's no elements, so the size is 0, right? And there is no top node, so the pointer to the top node is null, right? Don't forget, return the newly allocated object back to the caller so that they can actually use it for something. Right? Okay, size and is empty. These are dead easy to implement, right? Just like they would be in Java, right? To return the size, well, we're keeping, to return the size, we're keeping track of the size in the structure. So that's just S arrow size, right? Is the stack empty? Well, that's the same thing as asking, is the size of the stack equal to 0, right? Again, in Java, it'd be exactly the same code, right? Replace the arrow with a dot, and you've got Java. Okay, what about push? Guess what? It's exactly the same as in Java, right? So in Java, you make a new node, right? So what do you do in C? Well, you allocate a new node, right? So instead of writing node n equals new node, you call malloc, right? How much memory do you need? Well, I need the size of a new node, right? Once you've got your new node, what do? You set the element of the node, right? So I want to push that onto the stack. So I take that element, assign it to the elem member of our node, right? What do I do next? I need to take this new node and I need to hook it up to the current top node, right? So I need to set the next link for the node so that it's equal to the current top node, right? Our current top node is just stop. What do I do next? Well, stop points at the top node. I've got a new top node, so I better adjust stop. Right, so that now points at n, right? And I've just added a new element to the stack, so I better increase the size of the stack by 1. Right, finally return s to indicate that push worked the way we expected it to. Again, notice here we return null if there's an error. Right, so let's push. So pretty straightforward, right? Again, if you were to look at the Java implementation of this, it's more or less the exact same. What about pop? Okay, so pop's a little bit more complicated than the Java, than the corresponding Java code, right? So when you pop an element off of stack, you have to remember not only do you need to return the element back to the caller, right? But you're getting rid of a node from your stack. And the way that you got the node originally was that you allocated memory for it. So now you have to free the memory that you originally allocated. So there's going to be a call to free somewhere inside of pop. So step 1, I'm going to remember what is the current top node. The reason I need to remember that is because I need to get the element out of it. And I'm going to delete that top node in just a second, right? I'm going to free the memory associated in a moment, right? So I'm going to remember what the old top node is. I'm going to grab the element out of the top node, right? And now I need to make the current top of our stack point at the next element in the sequence, right? So I need to make it point at the second element in the stack, right? How do I get the second node in the stack? Well, that's the old top node next, right? So stop is now equal to the next node in the sequence, right? I can now decrease the size of the stack by 1, right? I've got all the information I need from the old top node, so I can get rid of the top node now. Right? So I can free the memory belonging to the old top node, right? Everything's fine, right? And I can write the popped element into the object that the caller has passed me. Right? So the caller has passed me the pointer to an int where I can write the value of the popped element into, right? Our function is a little bit sophisticated, right? If the caller passes in null for popped, then we don't write the value into the, then the caller is telling us they don't care about the popped element, right? They want us to pop the stack, they don't care about the value, right? So we don't write into that object. If that object is not null, then the caller is telling us, hey, please give me back the value, right? So dereference the pointer, assign the value elem to the object being pointed at by popped. Right. We're now done. Return the stack to indicate that everything has worked the way we expected it to.